maybe I record first. Yeah. So good evening. Today we are going to launch our tutorial on ENGY610. So today our topic is about the electric. Let me share. Seems I can't share. A moment. Yeah. So let me share today topic, the electric motors and drive. So I believe you have attended the lecture just last week. Am I correct?
Yeah.
Okay. So
but we discussed about the heating.
Sorry, I beg your pardon.
We discussed about heating and the pumps.
Okay.
Yeah, and
Okay. Understand. And I also follow your syllabus. And today, our main focus is the assignment. The assignment which we are going to take a look is on the textbook. Let me
okay.
Regarding to 7.1 to 7.9. Today is quite a lot of questions, but it's not difficult. So it won't take a very long time for each question. So don't worry about that. So for the first question, is about an AC induction motor, has a full load speed of 1,475 RPM. So now, what is no load speed? So for the first step, we need to figure it out. What is the relationship between the low load speed and the full load speed? Because the question just state the full load speed and nothing. You don't have any information like the power of the motor, the torque, or any information like current, voltage. You don't have it. Just the full load speed, and you need to find out the low load speed. But I'm sure there is a relationship. If you still remember, the relationship between the full load speed and the low load speed is 2 to 3% lower than the low load speed, which is the full load speed. So we make use of this relationship, try to calculate the range of possible low load speed of the motor. So 1,465. So what is the variance if it dropped 2%? That means only maintain 98%. So I make use of this equation and figure out the range of the low load speed range between 1,510 and 1,495. But it's just a range. But now we need to find out a number, a low load speed number. So what should we choose? 1,500 or 1,501 or 2 or 3? So we need to rely on the second idea. Is the equation between the speed and the number of pair of poles and the frequency. So the equation is speed is that means RPM in terms of RPM, which is equal to 50. 50 is a constant. No matter you are located at North America, Asia, European country, still 50. But frequency may variance. In North America, the frequency is 60. But in some part of Asia or European country, it will be 50. But we assume as we are in Canada, so we make use of the frequency of the North American standard. So which is the frequency is 60 Hertz. So number of pole. Also in the question, there's no information to given what is the number of poles. By the way, I want to insist one thing about the N here. N here is divided as the number of pairs, pole pairs. That means if you have a motor, it is 2 pole. So number of pole pairs, which is 1. Okay, don't mix this concept. If the number of poles of the motor is 4 and the number of pole pairs is 2, okay, which is divided by 2. So this point is very, you need to pay attention. N is not stand for number of pole. It stands for number of pole pairs, which is need to divide by 2. So let's put the because all the times the motor should be start with the number of poles by 2, 4, right? And 8. And so number of poles here, I put 2, and number of pole pairs is 1. So N is equal to 1. So by this equation, we can figure it out. The load speed, no matter you will obtain 3,000 RPM or 1,500 RPMs. So combining these two ideas, so you know the range of the load speed is range from 1,495 to 1,510. And other option is 3,000 is too far away from the range. So we can eliminate it. And so the remain is 1,500, which is also in the range between these two numbers. So we pick the standard number, 1,500 RPM. Okay? So any question on this? Okay, so if no, maybe we switch to question number 2. Question number 2 is asking the efficiency of the motor. When we handle such kind of question, we need to call out what is the definition of the efficiency. Efficiency is the output over input, which is very, very basic concept. So the output for the motor is the mechanical power, and the input is electrical. So motor, the energy transfer is from the electrical and transfer to mechanical, okay? And also, of course, the heat or friction or whatever, okay? But mainly is the mechanical shaft output, okay? So the question is, a 20 kilowatt AC motor operates at full load and draw 25 kilowatt. What is the efficiency of the motor? So we also in our mind, we have this equation, and we try to substitute the number in these two parameters. One is output. So 20 kilowatt AC motor operate at full load. It already tell you the motor right now at full load. Full load, that means it connects something and the motor is operating. So it draw 25 kilowatt, which is the input. So the motor draw 25 kilowatt electrical input, and that maintain the motor at full load speed. The power rating is 20 kilowatt. So the electrical power input is 25 kilowatt and mechanical power output is 20 kilowatt. So by the definition of the efficiency, and we can obtain the number of 80%. Okay, it seems it's not so difficult on this question.
Yeah.
And any question? Okay.
No, no question.
Okay, very good. Then we go to number 3. Question number 3. In question number 3, it carry another concept is load factors. So what is load factors? By the definition of load factor, which is the actual shaft power over the maximum shaft power. So you need to know, even I have 1 horsepower motor, but sometimes when it operating, it may not to draw the capacity of the motor, especially for the motor in a continuous one. So all the times we will think about the duty cycle of the motor is how the motor operated. You need to continuous one for a very long time. For some of the application will happen like this. But for some of the application, it may turn on 5 seconds, turn off 5 seconds, turn on 5 seconds, turn off 5 seconds, or turn on 5 seconds and stop for 10 seconds. Is a kind of duty cycle. So, of course, in the economic standpoint, we will not over quality when we design the motor. So, even we design the motor, let's say in this question 30 kilowatt, but most likely, especially the motor in the continuous one, that means turn all the time, turn. Like what is the application? Like in the summer, your friend, it will not stop because it's very hot. You need to turn on and the friend rotating, maybe overlight. So it's a kind of the example. So if we need to know what is the status of a motor, so here the load factor will tell you what is the loading situation of the motor. So now this question, 30 kilowatt motor is connected to the pump, but the pump will not draw all the power of the motor, just 15. So by the definition of the load factor, which is the actual shaft power, that is 15 kilowatt because it connected to the pump, and over the motor itself, the power rated, that is 30 kilowatt. So the load factor is 15 over 30 times 100%, that is 50%. Okay? Any question on that?
It's clear, yeah.
Okay. Okay. So we go through much likely two factor. One is efficiency, one is a load factor. Okay. So here, which is like a revision on the power factor. Actually, for this question, it's not much about how to calculate the motor, but it's more trying to make a revision on the power factor. Here, the question is about three phase. The motor in problem 7.2 that we have already go through this one is a 20 kilowatt AC motor operates at the full load and draw 25 kilowatt. So output shaft is 20 mechanical output is 20 kilowatt, and the electrical input is 25. So because we need to make use of this information, okay, in problem 7.2. Now is three phase, 380 volt motor that draws 40 amps at full load. What is the full load power factor of the motor? So first of all, when you read the question, you know three phase, the three phase will catch your memory that immediately root 3 times V times I, and of course with the power factor and times the power factor will appear in your mind. So second, we need to know what parameter, what number we have already got. One is 380 and draw 40. So in this equation, we already know it's 380, I is 40. Then we can put the number here. But now we need to know about the power factor. We know about the total power is 26.33. That is our of course our apparent power. Try to imagine a power triangle. By calculating root 3 times 380 times 40, that is the hypotenuse, the slope, the value of that. That is what we have already got, already calculated is 26.33. And so we know this, and now we need to have the power factor. But what is the real power? If we know the real power in terms of kilowatt, and we have already got the number of kVA, that is apparent power or total power, then we can obtain the power factor. So as this question needs us to find the value in the problem 7.2. So now we are not going to calculate the efficiency. We need to calculate the real power, apparent power, which is electrical related. So refer to this one, we shouldn't take the mechanical power, because if we take the mechanical power, we also consider the efficiency. So we only consider the electrical power input, that is the real power, because now in 7.4, we are going to calculate the power factor, which is no efficiency related in this question. So we take 25 instead of 20. So 25 as the real power in terms of kilowatt, and over 26.33 that we have already calculated here, and we can obtain the value of 95%. Okay, or 0.95 for the power factor cosine theta. Okay, any question on that?
No, it's good.
Oh, okay, good. So I would say even today there are many questions, because at the back of your textbook in chapter 7 is from the question is 7.1 to 7.10, but I read your syllabus, your things to do, you need to prepare for 7.1 and 7.9. You have already done almost all the questions, just one question left. Okay, so 7.5 is a 40 kilowatt AC induction motor, has a full load speed of 1,460 RPM. The actual running speed was measured in a manufacturing laboratory at 1,475 RPM. That means the induction motor, the full load speed is bar A, that is 1,460. But the actual running speed was measured in the manufacturing laboratory. That means during the calculation or the nameplate, theoretically, the full load speed should be 1,460. But now, what I really measured when the shop is running, we make use some meter to measure the rotational speed. That is 1,475. It will have a variance, of course. It will not have exact number. So the manufacturing lab tells us that molten load factor will be the ratio of the low load speed minus the actual running speed divided by the low load speed minus the full load speed. That is the equation. So I try to simplify this sentence from the and to here, just regarding to this equation. Okay, now what we have already got is the full load speed. Okay, this one we know about that. Actual running speed, that is by the measurement 1,473. We have already got it. So if we know one more parameter, that is the low load speed, then we can get the number of the low power. So as you try to remember about the first question we have discussed just maybe 20 minutes before. So we just have one full load speed, then we can obtain the low load speed. We make use of the same methodology and calculate the low load speed. By the full load speed, the relationship between the full load speed and the low load speed, 2 to 3% lower. And we can obtain the range here. And also, we making use of the equation 50 times frequency over the number of pairs, that we can get 1,500. Okay, so by putting all the number in this equation, then we can obtain the load factor, which is 67.5%. Okay, any questions?
No, it's good.
Okay, so now we are going to take a look on 7.6. So 100 nameplate kilowatt AC induction motor. That means the nameplate and stated that it is 100 kilowatt and has the load factor of 70% and the efficiency is 92.3%. What is the kilowatt input to the motor? So that is one equation. Immediately you need to recall it is the equation related to the nameplate, kilowatt, the power, and the load factor and the efficiency. Then you can obtain the power input. So just putting the number, load factor, 70%, efficiency, 92.3, and the nameplate power is 100 kilowatt. And put the number here, and we can obtain the power input. Okay, which is not very difficult. Okay. Any questions?
Can you explain once again
Okay.
step 2?
Oh, this one.
Pythagorean.
Any questions?
No, go ahead.
Okay. So 7.7. That is the same question as the power factor, but it is quite similar to what we have done already. A three-phase 380 volt AC induction motor draws a current of 80 amp and has a power factor cosine theta, that means the cosine theta of 95%. So what is the kilowatt, the power input to the motor? So by the definition of the power in three phase, that is √3 times voltage times current, and also times the power factor, we can obtain the kilowatt, the power input. So we put all the numbers inside, and we also know this is the total power. But now we need to know the real power input, the power input to the motor. That is the real power, not the appearance power, not the total power. Is a real power. So now we can calculate the total power by 380 volt and 80 amp with this equation. And also we know about the power factor, 95%, that is 0.85. Then we can obtain the power input to the motor, that is 44.76 watt. It's quite a kilowatt, which is quite simple for that one. Any question?
Yeah, it's good. No questions.
Okay, so this question, I think it's worth for us to go through in much detail compared with what we have already discussed. Is a question about the power factor correction. And AC induction motor draws 100 kilowatt and has a power factor cosine theta of 75%. So now we know about the power 100 kilowatt. And for this, according to the unit kilowatt, that it also tells us 100 kilowatt is the real power, not apparent power or reactive power. Why? Because if it is the apparent or total power, the unit should be kVA instead of kW, okay? So we know the horizontal value, the real power, is 100 kilowatt. And the power factor is 95. That means cosine theta is 0.75. Now we need to know how many power, the reactive power, I mean the kVAR, that means the reactive power, okay, by consider this unit of capacitance should we put on the motor to get the power factor, which is up 85%. Somehow, when you have the appliance, which is have a low power factor, but you don't need to get the penalty from the power station, you not need to improve it in order to make a lower cost on the electricity bill. We need to connect the capacitor parallel to the motor. But what is the specification? How many power of the capacitor we should put in order to fulfill this situation? That is what we need to do in these questions. First step, we need to construct the power triangle. So the power triangle is, we know the horizontal, the real power is 100 kilowatt. And the power factor is the origin before, it is 0.75. And we need to optimize it to the power factor 0.85. And now we need to find out this value, the before reactant power and minus after reactant power, okay? So we know the power factor, we know the real power, then we can calculate the slope, the total power, by this definition. So the total power of the total power before we make any improvement, that is the real power over the power factor. Real power stay the same, 100 kilowatt. And the power factor is still 0.775. And we put the number here and we can obtain 133.33 kVA as this value, the apparent power value. And the second is the apparent power after we make the improvement. We put the capacitor, and because we have already know about the power factor after the improvement, and we already know about the real power, so we make use of the same equation. We can obtain the apparent power after the improvement. Okay, so we know this value, we know this value, and now we also know this value. Okay, so far, do you have any questions?
No, it's completely clear. Yeah.
Okay, so we make use of the Pythagoras theorem. That is the square of the horizontal value plus the square of vertical value is equal to the hypothesis value, the square of it, the square of the total power. So, but now we are going to calculate the reactive power. So we just do some rearrangement on Pythagoras theorem. So we can obtain the reactive power for this large triangle, for this square of the total power before minus the total the real power square, then we can obtain this value, the whole range of the vertical value. And we do the same step to obtain the reactive power after the improvement. So by subtracting the reactive power before we make the improvement and minus the reactive power, then we can obtain what reactive power capacitor we need to add to the system. Okay. So any question on that?
Oh, no.
Okay. So now we jump to the final question on these electric motors and drive.
1 second, can you
Okay.
move the slide back? Yeah.
Sorry?
Can you move one slide
Okay,
back?
please. Okay. I can move one. So the number is from here.
Next.
Yeah.
The last step, yeah, step 4. So reactive power KVR.
Yeah. This
Okay, yeah,
one
got it.
is calculate from the overall, the before. The overall, that means the before we make any improvement, what is the reactive power, and minus our target after. So right now we actually find out this value, this subtract this, and we find this value. Okay.
Yeah, got it. Yeah.
Okay, very good. Okay, the last question is about the load vector, about the efficiency of the motor. So a 40 kilowatt motor with a load factors of 75% and an efficiency of 89.3% will be replaced with 30 kilowatt motor with a load factor of 100% and the efficiency 93.6%. How many power kilowatt of the power saving will be obtained from this project? So such kind of the idea is, I have a big motor. As I mentioned, sometimes if we keep everything safe, of course, the application may just need the power of 30, but I try to keep everything safe. I make the motor larger to ensure it can run without any problem. But we need to pay, because larger motor, higher power rating of the motor, you will pay more than the normal fit size motor. Okay, so this question is, before I have a quite large motor, so the load factor you will know, it may not fully utilize of the motor, just 75, and the efficiency of this motor is comparatively not very good, but is fine, 89%. Now we change the motor, a smaller one, but I try to fully utilize this motor, this load factor of 100%. And the efficiency is higher, maybe it's new one, better performance and better quality, or higher level of the technology, whatever. So we switch from large motor, old motor, to small new motor. So we need to calculate the power saving. If you still remember, we have touched with one question, which regarding to the load factor and the efficiency. So we make use of the same concept of load factor and the efficiency. We divided it into two cases, before and after. So before, we put the number 40 kilowatt of the motor power rating, 40 here. And load factor is 75%, load factor 75%. And the efficiency is 89.3 here, efficiency. We can obtain the motor in the past. So in the old time, we use this configuration. And now we switch to the new one. And the power rating is 30 kilowatt. And the load factor is 75%. And the efficiency is 93.6%. So we also put the number to this equation and obtain the value. By subtracting the situation of the power usage before and the after, then once we subtracted it, we can obtain the power saving value in terms of the kilowatt. Any question on that?
No.
Okay. So as I say in this chapter, even we have already done 9 questions, 9 out of 10. It seems a lot, but if you can obtain a concept of first, what is the relationship of the full load speed and the low load speed, definition of the efficiency, mechanical power output, and the electrical power input. The load factor, what is the load factor? It's the actual shaft power over the maximum shaft power. And it almost contains all the elements in our textbook, in our syllabus, that is in the electrical motor and drive. But also, you need to get a very good handling on the power factor, no matter it's single phase or 3 phase. So if you can obtain those ideas, I believe you can fully answer all the questions in this chapter. But one thing that is a reminder on the equation of another other presentation on the load factor is a low load speed minus actual running speed over low load speed minus the full load speed. If I remember even in your notes or in the books, it have this equation, but try to also remember this question and know how to use it, because somehow it just gives you the speed, then you need to calculate the load factor. If you can handle those relationship, load factor, efficiency, and the power factor, then almost all the questions here you can settle. So I think I have completed all the questions today. Any question or any topic you like to go through?
Well, no, it's good. It's okay.
Okay. So thank you very much for your attention. So I think we can stop here and have a great evening.
Yeah, thank you so much.
Okay, thank you very much. Thank you. See you. Bye.
See you. Bye.
Bye.